And so now we can move on to thinking about p orbitals. We now have two ways to talk about p orbitals. We can talk about the wave function squared, the probability density, or we can talk about the radial probability distribution. So when we talk about p orbitals, it's similar to talking about s orbitals, and the difference lies in now we have a different value for L. So L equals 1 for a p orbital, and we know if we have L equal 1, we can have 3 different total orbitals that have that subshell of L equaling 1. So we can have, if we have the final quantum number m equal +1 or -1, we're dealing with a px or a py orbital. Remember, we don't do a one-to-one correlation because px and py are some linear combination of the m+1 and m-1 orbital. And if we talk about m equals 0, we're looking at the pz orbital. And the significant difference between s orbitals and p orbitals that comes from the fact that we do have angular momentum here in these p orbitals is that p orbital wave functions do in fact have theta and phi dependence. So they do have an angular dependence that we're talking about. And what I'm showing here is not on your notes. If you're interested, you can look it up in your book. This is a table that's directly from your book. And what it's just showing is the wave function for a bunch of different orbitals. I mentioned last time that there was this list in your book. And what I want to point out here is this angular dependence for the p orbitals, for the L equals 1 orbitals. So first, if I point out when L equals 0, when we have an s orbital, what you see is that the angular part of the wave function is equal to a constant. So remember, we can break up the total wave function into the radial part and the angular part. When we look at this angular part, we see that it's always the square root of 1 over 4 pi. It doesn't matter what the angle is. It's not dependent on the angle. In contrast, when we're looking at a p orbital, so anytime L is equal to 1, and you look at the angular part of the wave function here, what you see is the wave function either depends on theta or it is dependent on both theta and phi. So we do, in fact, have a dependence on what the angle is of the electron as we define it in the orbital. So what this means is that unlike s orbitals, p orbitals are not spherically symmetrical. They don't have the exact same shape at any radius from the nucleus. And these shapes of p orbitals probably do look familiar to you. Most of you, I'm sure, have seen some sort of picture of p orbitals before. So what I want to point out about them is that they're made up of 2 nodes. And what you can see is their nodes are shown in different colors here, and those are different phases. Sometimes you see this written when you see p orbitals. One is written as plus, one is written in minus. That's not a positive and negative charge. That's actually a phase, and that arises from the wave equation. Remember, when we have waves, we can have positive or negative amplitude. When we talk about p orbitals, the phase of the orbital becomes important once we talk about bonding, which hopefully you are happy to hear at the beginning of class we will get to soon. And it turns out that when you constructively have 2 p orbitals interfere, and when I say constructively, I mean they're both either positive or they're both the negative lobes. That's when you get bonding. Whereas if the phases were mismatched, you would not get bonding. So that's going to be important later when we get to bonding, but just take note of it now. We have 2 nodes, each with a separate phase. Or we have 2 lobes, each with a separate phase. And when we look at this, it's actually split by what's called a nodal plane, which is pointed out in light orange here on this picture. But what we just mean is that there is this whole plane that separates the 2 lobes where there is absolutely no electron density. So the wave function at all of these points in this plane is equal to 0, so therefore also the wave function squared is going to be equal to 0. So if we say that in this entire plane we have 0 probability of finding a p electron anywhere in the plane goes directly through the nucleus in every case of a p orbital. So what we can also say is that there is 0 probability of finding a p electron at the nucleus.